Hello, everybody. Sorry, I didn't connect the audio. Here we are. We had assigned a little homework. Let me remind you what the formula, I wrote it. The formula for CS production function is this. Where I call A, what's usually called rho, but rho is too fancy. And A is either. Do you recognize it? Does everybody recognize the production function? Yes or no? We'll spend some time on this today. We'll use it as my friend Deidre would be happy because today we're going to teach a parable. She says she thinks economics cannot be very precise. We cannot teach parables, metaphor, use rhetoric. And so today we'll use rhetoric and metaphor. In general, I don't think she's right in the sense that she exaggerates. Often we teach parables and metaphors, but other times we can teach things that are specific. And there are micro data, macro data that can do precise growth. No, I don't think we can do growth precisely, not even remotely. So let's use the parables. But first, let's see if anybody has worked out the exercise. No, not good. Never going to go far in life if you don't do the things. Okay, well, let's start from here. I know you're thinking, Jesus, my father used to say that. My grandfather. My grandfather. So we had started from here. I was trying to teach what? Teach that the problem of growth as a matter of accumulating things has long been solved, at least in the representational terms. And you see, that's the other interesting. So Solow says, look, I'm studying the stability of a stationary state because some people, Harold Domar and their followers, say that the stationary state of a market economy is not stable. It breaks up continuously, either into human catastrophe, millions of unemployed people, or economic catastrophe. Companies that collapse because there is capital, but there are no workers. Okay, and so the return on capital goes to zero. You don't have people working for you, you cannot do much. And he says, no, that's an exaggeration. There is some form of market mechanism or near market. Oh, you're right. Alessandro, thank you. I get too concentrated on the class recently, and I forget the fact that there are few people listening to us still online. Sorry. I apologize. So now you should see it. And it says, let me give you a little argument. And you see that of Solow is also a parable. It's telling a story, an allegory, if you want to be classically taught. It tells a story. The story has a mathematical representation, which is like a way of describing it very shortly, but you can describe it in words. And the story is, to the extent that you can change the techniques you use from certain technique that uses a lot of capital and little labor to another one that uses less capital and more labor, then when there is little investment, little ability to invest, and there is a lot of labor, you will have any scientific techniques that use a lot of labor. That will make the salary not very high. Because when you have a lot of labor and very little machines, you tend to have very inferior technologies. Notice that these days people will say 50 years later, right? 5 years later, oh, maybe not. Right? I have very productive machines. We use very little labor, but it's very productive. So one has to be very careful with this story, right? And use a lot of labor. So there would be no human tragedy. Vice versa, if workers are really scarce, they become very expensive, then you will make an effort to replace workers with machinery. You will invest more, that will allow you to still employ the few workers profitably. That's Solo's. And because he's doing that, he says, I don't want to study an economy that grows forever. That's a too nice story. I mean, we're talking about disaster, right? We should talk about an economy that grows forever. And he puts in a footnote that observation. But obviously, if he puts it in a footnote, it must be, so here is the part of the course that has to do with history of economic thought. It must be that everybody knows. 170 people in the whole world that in 1956 are actually reading that paper. It's probably not a number larger than 200. Okay, it was not a paper, not popular, like 50 Shades of Grey. A lot less, a lot sexier, I think, and pornographic, but a lot less popular. And she puts in a footnote, and everybody says, "Oh yeah, Bob, we know that." Right? That's the point you have to get in. So when 30 years later somebody comes out and says, "Oh, you cannot have growth with decreasing return," this somebody must have not read Solomon, let alone the other where that thing is being explained quite carefully. Oh, it's growth as I explained the other. What is the point of that? Then we'll do the exercise together. The point is that clearly returns, increasing, don't matter for growth, per se. They don't really matter. Think about it. It's very extraordinary that people keep thinking at increasing return as the source of growth, when increasing returns has a very clear meaning. It means the technology is such that the more you put labor on whatever activity, the more productive it becomes. And there is no example. Every example goes against. Remember, you're too young, but you go read the history book. You know, the plants of Soviet Union were very big. Some employed hundreds of thousands of people. Were they more productive? No. One implication of this theory is that says, it's a bit, what's the name of that porno actor guy? That's if size matters. You see, increasing return says the size matters. Maybe. But maybe not. Doing it right matters. That's chronological. Because if you look around, if size matters, then small countries where this external effect, increasing returns, is by definition impossible, like Luxembourg or Switzerland or Ireland, they should have never grown. Growth should always have taken place in India, China, they've always been bigger, or Russia, if you want to stay on the west side of the Europe. Well, it didn't. It took place somewhere else. But it took place initially in places so small, like Florence, Venice, the Netherlands. You say, okay, but that was before the Industrial Revolution. We're talking about post, okay? England was not very, you know that England was a very unpopulated country? You know the population of England was about, let me try to remember, but I think a third of the population of France in the 18th century. England has a population explosion in the late 18th century and the middle of the 19th century. Really an explosion, huge demographic transition. But France is much more populated, and Italy too, in the 18th and also for good part of the 19th century. So whichever side you take, it doesn't come out. And given that we're teaching foundation, that is, we're trying to grasp the logical basic elements of economics, if we define returns as being taking a technology and increasing the size at which you use it, then by definition, it cannot happen. By definition. Okay? But we spend a lot of time. But it's not only this. The other thing I want you to think about, that's why we have an extra class on growth, is that all these models, including solo story, for Neumann, exogenous, endogenous, all the stories that come out from New Growth Theory, which I will tell you in a moment, are, in fact, we call them theories of growth. I think we should call them stories of growth, not theories. They're description. Now here I'm being a bit, I would say, philosophical, okay? But actually what I'm trying to do is try to understand in what sense the tools we use can get us to causes. Think about what you do in biology or physics or other things. When you go to the cause of a virus, for example, right? You try to catch, not caught. After you have caught it, you all try to open up under the microscope this little object that you call a virus and you understand to be the cause of this reaction your body is having. And you decompose it in its component, look at it, say, oh, it's made of RNA. RNA works like this. These are its chemical components. So your explanation is a reduction of the macrostructure, the virus, to some microstructure and to some microstructure, up to the point in which you think you can control them. Right? Up to, say, at the protein level, even below the molecular level, which you say, okay, I can control that. I know the structure of that protein. I know how to make it up, and I know what to do. And you say, okay, I have a theory of why. Okay, that's what we do. Now, if you think at it a moment, you realize that this thing that we accept as a theory, and I accept it too, I'm happy with it. I don't think we can do more than that. It's a theory, so to speak, from the point of view of the way old people would think of a theory. Because people would think of a theory as discovering essences, raison suffisante, right? Ragione sufficiente, sufficient reason. Then they always ended up with God. Sufficient reason, pretty much anything. And so I never understood why they studied. They already had the answer. Why do you study if you already know where you're going? But the point was that the idea of having a theory was like there had to be a discontinuity, a jump, right? Between what I'm trying to explain and what explains. We use the Latin words if you want, so we look like we went to the classical museum, but we're all modest people. So we don't use explananda and so on, right? In these theories, what is that you do? In the physics or biological theory of the virus, you go down, it's a reduction. You go down to its component. Up to the point at which what? At which you can control things. You're happy when you say, hey, no virologist goes deeper than the structure of the virus. It says, oh, let's explain the protein. Yes, you can explain the protein and they say that you come up with its molecular structure, but that's what you do. And you explain the moleculars, but that immediately gets you out of virology or biology. And you give it to the chemist. It says, oh, the chemist, oh, you tell me about the moleculars, right? And then the physicists come around and says, give me the atom. I'll take care of the atom. I break it up. But they end up studying other things. It's not much information about a virus in somebody telling you, oh, you know, there is the strong force, the weak force, and that works and this. Okay, that's good for the virus, and it's good for the ice cream as well. And, you know, it doesn't really tell me much about the difference between virus and ice cream. Why am I giving you this? Because think of these theories. In what sense are they theories? In what sense do they break down growth into its component you can control? They don't. They tell you a story. Smith and Ricardo told you the following story. There is no growth. We accumulate, then eventually we get a certain set of machines, a certain amount of capital, a certain amount of labor, a certain amount of land, a certain ratio. They live happily forever. and they get their rewards, the income distribution, the price. That's their story. And then, I mean, Smith tells you some good gives you some good speeches, some preaches for Sunday. Oh, you know, you want to grow rich, you have to let people try. They're not generous. That butcher is not generous. He's selling you the steak. That's why he froze it on the scale, because he wants to add 50 grams and sell you a smaller steak at a higher price. But, you know, even though he's motivated, he gets you good beef. And so is the bakery. And that tells you a story, but it's not a model. It makes you think about things. I'm not saying it's useless, but it's not like the biologist telling me, oh, the virus is telling me something different. And so on. And Marx tells you a story, and Ricardo, and then Solo tells you a story. He says, well, you know, there is technological change, which means it doesn't really depend on how much capital we have, how much labor. It depends a lot on this thing that I can measure. It's called TFP. You see, it's a residual. We don't really know what it is, but it grows at 2% a year, 3% a year, 1.5%, depending. And good. But is that a theory? One has to be careful to call these things theories. It doesn't break down. So the only thing, that's why I put this here. See, modeling innovation or mimicking productivity. We're not really modeling. We are mimicking productivity increase. It's like, you know, it's like, I forgot, I think it's the Japanese theater. Kabuki. The theater of shadows. You ever seen it? It's very fascinating. You ever go to Japan or you have a chance to go? It's theater by shadows. The actors are behind the screen and the lights, and you see the shadows. That's what we're doing. We're projecting shadows of growth on a screen through the formulas and the stories and the statistics. And I am not saying that it's useless. It's important. I'm not trying to put down this. I am trying to say be aware of what we explain. Our explaining is very different from what people studying black holes. Eventually, everybody stops. The physicists also stop. So that when you go, oops, Big Bang, gravitational, strong force. Why? Because that's it. That's the way it is. You happy? Well, tough luck. If you're not happy, you got to put up with it. That's all we can say. Okay? So let's be careful. Says the economists, we stop a lot. To say, okay, here is a picture of what's going on. Oh, no, obviously it's scientific. What does scientific mean? I mean, I put my best effort. I use my brain. I'm not stupid. Kenaro was very intelligent. Trust me, I saw him debating Murray Gell-Mann and some of the most intelligent physicists and mathematicians on the face of Earth. Ken was at an IQ comparable or faster. So he wasn't stupid. We always check this data. I check my data. I'm happy to talk about data. The mathematics is right. Oh, it's scientific. It's not some bio blue, blah, blah, blah. I mean, no, I'm serious. It's scientific. I'm just saying that that's the best we can do. Scientific doesn't mean super duper. It's not like super green pass that Draghi yesterday imposed upon Italian in one of the worst performances of his life. Yesterday, it reminded me of Conte for a moment. I had to write it. Please don't do it again. Please. I want to be proud of it. Okay? So it's scientific. It's just that it gets there. It doesn't get any farther than that. That's all. That's all. Saying the level at which sociologists, economists, blah, 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 explain is this. Not far. So if you're interested, tomorrow, Veniceman has organized a nice debate on a famous book about very long run growth, which is the book by Jared Diamond on guns, germs, and steel. Cannoni, Germi, Acciaio, I suppose that's the Italian translation. And you will see that's all. He has a theory of long run growth, really long run, thousands of years, and why Europe and China are ahead of the pack. And it boils down, he tries some reductionist thing. He counts it boils down to zebra versus donkey. Basically. If you have a lot of zebras, you are unlucky. If you have a lot of donkeys and pigs and chicken, then you're lucky. Well, if you're curious, get asking management to give you the Zoom thing tomorrow. Okay, but that's what we do. Okay, I just want to warn you. So what we're calling theories are certainly causal explanation, but the level at which the thing that explains the cause leads, and the levels at which the thing that needs to be explained are very near. They're not as far away as quarks and stars. Quarks and stars are very far away. Isn't that fascinating? Think this crazy damn idea that the fact that you're heavy modifies the space-time, it slows down. That's it looks. Now, obviously, notice that the reason why it's so fucking fascinating, it's because it's easy. That I think was Pauli. I remember it was Pauli, the other one of the first quantum guys, Planck. Maybe it was Planck. Planck is the one with the constant, right? Yeah. I think it was Planck that apparently had started to study economics and had case and then gave up. So it's too difficult. Well, if you look at it, it's honestly, yes. In fact, I think we should write a lot fewer papers. We should write 100, 1 divided 100 of the papers. We write a lot of stupid papers, bullshit about nothing. We know nothing. We keep repeating, I know nothing, but I want to talk. Just shut up. Right? So it's very difficult. But the only thing is that what we're doing is representing, not, I don't think we are really explaining. And probably because the explaining occurs at another level. We need to explain why human beings are so different on certain respect, from horses. Where does this continuous changing the natural setting in which we were given come from? And we understand that the obvious explanation is it comes from our brain, its function. Right? We change completely the setting in which evolution thrust us. Now I'm a bit Pythagorean. Okay? We did, and we are the only species that did that. Because all the others just live exactly, those that live in a different environments because we did. So we took the horses and moved them inside. And we took the dogs, were wolves, and changed them and turned them into chili cow, blah, blah. I mean, rats that you put in your bag and carry on the train, right? We did that. If it were for them, they will stay wherever they were born. But they never changed their environment. I mean, they changed their environment very partially. And an answer might simply be that that's all they could change. That there is, in fact, nothing different from the motivation and the functioning of the brain of a tiger and the brain of a human. It's just that the tiger can change its environment only to the extent of killing whatever she can kill or he can kill, right? And building up the savannah or in the jungle some angle to stay, and that's all. And so the tiger does what the tiger can do. So does the elephant. The elephant does whatever it can do. But their motive, if it were up to them, they'll also change their environment dramatically, as we have done. They're just unable to, because they don't have the hands, they don't have the brain, they don't have the communication, they don't have the language, all this stuff. And we do it just because by selection, we ended up having all these damn things. So that's it. And then that's the explanation. So that's what I want to teach you today, which was, if I want to tell a story of growth and I want to represent it, I want to represent it at the aggregate level, that is with simple variable, I can do it with one equation. You know, I'm wondering if this thing is recording. It's recording. One second. Sure it is. Yes, it is. Now, the thing so I ask you to concentrate on this thing, on this formula. It's a formula. Okay? So imagine this is aggregate output. This is just a number. Aggregate output is measured, for example, let's imagine a farming technology. Okay, so aggregate output is tons of grain. Okay, so it's measured in tons of grains. Capital is also grain, the seed. So that's also measured in tons of grain, but labor is measured in our work. Okay, and then there is some constant here that allows me to make this into a common factor. It's a change of unit of measure. It makes hours of work turn into tons of grain. Okay, and then we'll see what the parameters do. And then the big constant A says, in some sense, how productive is the land? Okay, so I'm taking the land here. I'm not writing the land. So to the extent I'm not writing the land, remember our constant return technology, right? I'm either saying land doesn't matter. That's a possibility. Or I'm saying, yes, land matters, but see if there is some intuition in this story that I'm making up about the farmers that are doing what farmers do. You know, they seed, they work, and then at the end of the period, they do the harvest. So if I don't put land explicitly, what is that I am actually saying? The opposite. It is. It's so abundant that it's not a constraint. It's abundant and it's all of the same quality. So that I have 1 unit of capital, 10 units of capital, 100 units of capital, millions units of capital. This is all the land I want. And it's all uniform. No Ricardo here, no decrease in returns. I can do whatever I will do today. I can do with 3 factors, with 75 and with 75 millions. Don't worry about it. It's just it becomes longer. And the symbols grow, so it becomes, okay? But one has to remember what one writes. You know, writing things has a meaning. That's why you put some discipline in your thinking by writing formulas, not because you are a fancy big mathematician. We're not. Not yet, because I'm a big mathematician. We're just small bananas, right? But because we want to put order, I write something that's simple, you see, few simple, and I have to think about it for half an hour, or an hour, whatever. This contains the land. It says it's good land, it's all uniform, no matter how many workers you have, millions of people, or 10,000 or 10, same thing, and there is as much as you want, so you don't have to pay for it. Okay? But it defines the scale, right? If A is small, I'll get little output. If A is a lot, I have a lot of output, so it means lands can be more productive. A defines its level of productivity. In general, we say, in fact, that A defines the level of productivity of a technology. Okay. Now, what do A, near mean? We use that parameter because this is a mathematical property. To understand what I say now properly, you have to do a little bit of algebra. Take some derivative, make some understand that what that parameter does is to, 1, measure the degree of substitutability between K and L. We'll see it in a moment. And 2, because I use A here, and A here, it defines the returns. In particular, in this case, it says that technology has constant returns. Now, this is a mathematical representation of a concept. The concept, we know what it is. The concept means that if I double or triple or quadruple or multiply by 1.756 K and L, the same thing happens to output. That's what constant return means. Please. Well, the fact that I use A on both and that I have 1/8. That's all two things are necessary. You will see in a moment. We'll play a bit and see. Hello, that we can make returns become different from constant by playing with A. Well, by playing with the exponent. Okay, good. So how do we check that the returns are constant because there are those A's? Well, we do a little algebra, right? We multiply, we write, instead of having K, we pretend we have 2K. Instead of having L, we pretend we have 2L. Then we replace. So then it becomes 2K at the power A. Everything at the power A, 2. Okay? Then 2L at the power A, also the 2. And then we use simple property. 2K at the power A is like 2 at the power A times K at the power A. Same is true for L. Then we collect the 2 at the power A. Can you follow me without me writing? I hope so. Okay. And at that point, we take the 2A out of the square parentheses, but it's raised at the power 1/8. So the A goes away. Boom, magic. We have 2 in front. And it's exactly double as before. So there's constant return. By doubling L and K, we double out. Now, assume that instead of having, so first change, instead of having 1 here, assume you have beta, or actually let me use gamma. And gamma is a number less than 1. Say it's 0.9. What happens? Do the same thing. Do some algebra here together. Let me create a new slide. So let's duplicate that. It's not allowing me. Oh, Jesus, it's so slow. It's on my side. University of Venezia. Well, I want to do algebra live with you, but it's not allowing me. All right, you guys still see what I have here? Okay, let me see. Hold on a sec. I'll take the sharing away and then I'll put it back. No. I can't edit. Back. Okay, I use Latex Notation. I have another program which is not used to do this thing on the Italian keyboard, which is a nightmare for mathematics. All right, this big. Okay, let me share. Okay, I suppose you see this formula, right? This sign here means exponent, okay? So this is the same formula as k at the power a, l at the power a, and this. So if here instead I have c, another number, and c is a small number, say c equal, is equal 0.7. 0.7 is a way of saying 0.7. What you do? Well, if you put lambda here, so you put, say, multiply every factor by d units, okay? Then it becomes like this, and this becomes like this. Okay, but now when I collect d at the power a and I take it outside, what is it I get? I get this thing. A times, sorry, that means d at the power c divided a, right? D at the power a here, you take it away. D at the power a here, you take it away. Then you collect, then you take it outside the parentheses, and it goes at the power c, and then you get this. But if c is less than a, right, that number is not 1, right?
Prof, the a should disappear.
Excuse me?
The a in front, so d to the power of c should be, right?
Very good, yeah. Oh, yeah, I take it out. So this, the a disappears, you're right. This goes at the power, sorry. This goes at the power c, and c is a number less than 1. That's what I wanted. In fact. Thank you for whoever suggested and corrected my typo. And so now we no longer have increasing return or decreasing or constant return. We have decreasing return because if, say, d was 2, we double the output, and c is 0.7, right? We have taken the root 0.7 of 2. The root 0.7 of 2 is smaller than 2, right? If we take a simple example in which c is 5, then it's the square root, 0.5, then it's a square root, and so the square root of 2 is smaller than 2. So what we have discovered that by doubling the inputs, we cannot double the output. Output grows, but less than that, and we call that thing decreasing return. For example, this would be the case, we could have written the function like this, if land was not homogeneous. If land was not homogeneous and infinite, if land was a factor that matters, then we could have decreasing return. Because as we expand K and L, we have to move towards land. And so that factor is finite. I take a worse land, and then productivity goes down, and then productivity goes down, then productivity goes down, right? So that's one way of representing decreasing return. Vice versa, if C is 1.7, then I have increasing returns. Because now I double the output, I double the inputs, and the output doesn't double, it goes up by 1.7. 2 at the 1.7 is a big number. It's bigger than 3. It's a number between 3 and 4. So the mathematical representation is useful because it makes you see the concept. That's why it's useful. It's a simple way of writing down the concept here. Right? So I will not discuss further. We could also play with the A, put A here and put a different number here. That also will have an answer, right? Because if I put A and A, then I can collect B at the power A. But if I have A and, well, I already use B, so I also use C and I also use D. So that's called E, in Italian, E. Then I can collect the common part, depending if A is bigger or B is bigger. But there is a piece that remains. That would have an effect on either labor, makes labor bigger, or capital bigger. It changes the return effect. So the point is that we can represent this idea we have of here, of increasing return, decreasing return by using those. By using those symbols. So now let's stick to this because what I want to do, my parable wants to use the constant return. Okay? Oh, mamma mia. Now, in order to understand why with constant return you can grow forever, I want you to go from this formula, from this formula to this formula. What have I done in going from the first formula to the second formula? I set L equal to 1. That's all I do. Alternatively, I have divided output by total labor. And I have written down the formula for output per capita, right? Because imagine, divide Y by L. You get output per capita, or per hour worked, or per worker. Well, if you divide the left-hand side, you divide also the right-hand side. So you have A divided L, right? But L at the power 1 is like L at the power A at the power 1 over A. I know it's a dirty trick, but that's the way it is, right? Square root of X at the power 2 is X, agree? L at the, good. So that what I can do is to bring in L at the power A, the denominator, and it would go, it would divide K and it would divide L, right? And I leave 1 over A outside. At that point, L at the power A divided L at the power A becomes 1. K at the power A divided L at the power A is the same as K over L at the power A. Well, let's call it X. Here I wrote K. Imagine it's a different symbol. Now it's capital per worker. And so now I have written output per worker as a function of capital per worker. Right? Now look at this function. What is that our theory in the sense of our hypothesis of constant return to scale, impose on that function? Well, B is positive. I brought it under. Why is B positive? Well, because we assume the labor helps production. So better be positive. We're negative, labor will hurt production. It's like having Arcuri. Arcuri labor hurts production. So you put B. But if you're a good guy, you put plus. Okay? Good. Just a generic Arcuri, not the one you have in mind. What do you think always about it? Say. Okay? So B is positive. That's the only thing I know. Could be small, could be big. You remember what we said before. It's essentially a way of turning hours worked into kilos of tons of grains. Could be any number. The only thing I know is that it's positive. How about the big A? Well, the big A has to be positive, otherwise from capital and labor, I get negative wheat. That would not be a description of production, or would be a description of production in a place very desperate that disappears very soon. So A is just a big positive number. And again, nothing else. Or maybe a small positive number if you're trying to grow wheat, but you're actually the land you have available is at the North Pole. Not gonna get a lot of wheat. Okay? How about A? On A, we can say a little bit more because, and this you have to believe me, I'm waving my hand, but you have to believe me like I am a priest. Okay, believe me. A is a way of representing substitutability. One way of seeing that is very simple, is set A equal 1. If A is equal 1, that function becomes very simple. It's AK plus AB equal out. AB is just a number. And the function says output is always something, because something comes from the land magically, automatically, even if we don't work at all, if we don't put any capital, which is reasonable. You always get some wheat from the field, even if you don't see it, because the seeds go around, the birds, all the stuff, right? That's the fixed amount. Plus an amount that grows linearly with capital. For every grain of seed, say A is 100, you get 100 grains of harvest. Okay? It says that output per capita grows linearly, but it also said, now when you put L different from 1, you go back to the original production function, that I can replace capital with labor in that production function at a constant rate. Every unit of capital I take away, when capital is 1, can be substituted by 1 divided B units of labor. Right? Look at this part of the formula, the one here where I'm moving the arrow. Set A equal 1. Reduce K of 1 unit. Huh? How do you keep the same total? You just increase L of 1 over B units. Today we are unfortunately here, so I do not have the board, but it's, should have learned this. It's called perfect substitutability. Everybody follows me? Online as well. So A measure perfect substitutability is equal to 1. If it is equal to minus infinity, it should be equal actually, because it can take a value minus. Well, there you need, I'm sure they have, some professor did it sometime, somewhere. You have to take derivatives, right? And you discover that there is no substitutability at all. It's the so-called fixed coefficient. That is, this function becomes y equal a times the minimum between k and bl. That's what economists call input-output. We have, you see, that's another representation. It's not a theory, it's a metaphor. It says the technology is such that it's impossible to replace even of a little bit capital with labor. Now, think about it. The whole thing is complete metaphor. Why? Because there is no technology that is just capital and labor. Every technology, even the one I used at the beginning as example, coffee, is a lot of things with a lot of other things. Right? The gas, the mocha, the coffee, the water, the person, the fire. And most technologies are in fact fixed coefficient. So they're input out. Try having a cup of coffee by replacing the water with your time. You put the mocha, no water, turn the fire on, put the powder, and wait. Just wait. You can wait for a long time. The best you can get is get water because you have to call the fireman. You're starting a fire. So most, please. We can reduce even to 1. It's all a matter at which level we want to tell our story. It's a story, right? We can reduce it whatever we want. It depends on the purposes. That's what makes most social sciences are about stories. The only effort we make is to try to make the story a little bit less imprecise. Right? When I write a function like that, how can that function possibly represent anything, even a very super poor farming economy? I have assumed land is infinity, lasts forever, wheat is all identical, the hours of work are all identical, there's no manure. This poor son of a bitch doesn't even have a few tools, so he's working the land with his hands or her hands. I mean, come on, right? It's a silly technology. The point I'm saying is that obviously when we decide to write formulas like this, we are adding a lot of words behind that. And we have to put a big label that says, careful, sophisticated equipment, handled with care. That's why I started this class 8 weeks ago, or whatever it was, 9, saying, remember the aggregate production function? Maybe we use it at the end, and we're using it at the end, because it's a very delicate tool, very sophisticated, right? And this is an example. Look how many explanations we have to give for this function. And say, no, don't interpret it in that sense. Right? So again, for a equal to minus infinity, we represent a technology with zero substitutability. My claim empirically is most technologies are like. For example, think about it. There's very little substitutability for a given technology between capital. Most technologies are fixed coefficients. Take a siderurgical plant. Make steel. The ratio between coal and iron is what it is. If you change that, you fuck up. Right? Steel comes of different quantity if you make a different combination of coal and iron. Actually, the quality of the coal has to be very clearly specified, and the quality of the iron, they cannot take generic. Right? So the temperature, everything is super. So what is that you can modify a bit? I don't know, actually. Right? Because the workers has to be there controlling what's going on and setting the time and the temperature. There's no substitutability. Every substitutability is a technological change. But this was something that people that wrote this stuff at the beginning had it very clear. If you study the way in which, in the old days of economics, people derived isoquants, we call them isoquants, like this smooth production function. They would do it. How you would derive will be with you in a second. How would you do it? You would, I need, no, I don't want that. Somebody knows how to, I need to draw a, I forgot, I never drew a figure with, right. Any of you knows? Unfortunately, I never did. Let me see. Slide. What is it? I can move up. Yeah, but the problem is that the people that are online don't. Right. Yeah, maybe I do by pointing because there is too much light. I don't think they see. They see this. Let's do this. So we get a black. You can use that. Doesn't go any further. Okay, you can see, right? Yes. Very simple. Remember? Okay, capital and labor. Right? And how do you get the ISO? When you say there is an activity that has corresponds to this rate. And if I take this much labor and this much capital, and I use this combination, I'm sorry, if I use this combination, I get a unit of output. Then you say, oh, there is another activity. It has a different combination ratio, but if I use this amount of capital and this amount of labor, I get a unit of output. And then there is a third activity that has that ratio. And if I use this much labor and this much capital, I get a unit of output, and so on. And I draw a bunch of them. And for each one of them, I pick the combination of capital and labor that produce a unit of output. And then I connect them. Let's say that in a factory, I can use a combination. And that's the unit isoquant. And I'm afraid our friends online can see very little, but they can see. That's the way we derive the isoquant, right? And we tell a story, we say, imagine, you know, like John Lennon, imagine all the people. We do imagine. Like on the famous island, I told you the story, you didn't laugh at the beginning. The story of the physicist, the chemist, and the economist say, imagine you have a can opener. Well, imagine everything is substitutable. Then you have an isoquant. It's a John Lennon type of science. You know, peace on earth, imagine all the people, let it be. Okay? That's the kind of science we got. Now, Mr. Katz. Poi facciamo esplodere. It's a public sector machine. Even the machine doesn't want to work. It's taking coffee breaks. All right. Aren't you having fun? Huh? Where do you find a guy like me? I'm sure all my colleagues are a lot more serious. All right. So you understand? No, I'm serious on this now. I say ironic things, but I'm serious. So this thing doesn't, I mean, it exists. I don't want to put it down. It's a very useful tool. For example, I can teach a whole class with that. Remember, it's very useful. I just write one formula and I go on. I go on for an hour and 20 minutes a day, hour and a half. I could go on for 3 hours. I've taught once in China, I taught entire course of Marxian economics. They didn't believe it. Then they liked it. So I became the official professor at the University of Beijing teaching Marxian economics. That's a big honor. That's how do you think I know the people of the Communist Party? Because I taught them Marxian economics. So that's what you want to keep in mind. Okay. So that being measured your degree of substitutability. And we have learned by mathematics that if we move A from minus infinity to 1, we go from 0 substitutability to mild substitutability. Once we get to A equals 0, we get Cobb-Douglas substitutability, right? So it substitute, we call it constant elasticity, and we call it unitary elasticity substitution, okay? And as we go above 0, as A becomes positive and goes toward 1, we get higher and higher until we get perfect substitutability, which is really no law. You can change as much as you want, always the same ratio. Because even with Cobb-Douglas, you know, when you go very high up, in order to replace, when you have very little labor and a lot of capital in that technology, if you want to replace a little hour of labor, you have to put a large quantity, enormous quantity of capital. And vice versa, when your technology is made almost of all workers and very little machinery, then then you have to do the opposite. Did I say it right? Yeah. Okay. In fact, you get this absurdity in certain cases. You see what I've done here with where I gave you the example with A equal 1. With A equal 1, the two factors are perfect substituted. And so with A equal 1, you can get output without any capital. There is some stuff you can produce with labor. Actually, if you think of this as some metaphor for the aggregate technology of an economy, it makes sense. It has to be like that. For sure it was like that. Kubrick told us, did you ever see 2001? Space Odyssey? See it, look at it, it's beautiful. It's a class in economics at the beginning. It tells you how you get the first investment by killing the other guy. You just raise a bone and you pull it. You say, Severino, here I come, Techne, bang! And you kill the other monkey and you create a capitalist right there, right there. Capitalist, violent capitalist, imperialist, everything. Just in Kubrick wasn't kidding. If you read it, actually, he had exactly that in mind. You really want to talk about that? Okay, here's where he started. That's technique. Okay? Technology changed the world. The guy grabbed the bone, was not even a guy, it was a monkey. And you just hit the other guy. Welcome to the world of capitalism. Okay? So that was a technology in which you get output without capital. You built your own capital. Right? But then in another cases, that would be completely absurd. Right? It's be very hard to say, I'm going to produce computers without capital. If that's the production function of cell phone, A equal 1, not admissible. So it depends. It's a very, how can I say, it's a very elastic, constant elasticity, elastic. Actually, the word constant elasticity, let me tell you a bit more of history of economics. The word constant elasticity is because if you do a little algebra at home, which at this point I would not ask you to do because you never do it, you're useless. Okay? But if you do a little algebra, which could be good for your brain, trust me, even for your hand, for your brain, right, your self-esteem, you can compute the elasticity of substitution of the two factors. You can go to Wikipedia and find mathematical definition. Compute it, and you will realize that this function has a very nice property. What do you mean nice property? Does it mean it's realistic? No, it means it's tractable mathematically. It allows to make computation. It overcomes Planck problem that says it's too difficult. He was right. Well, you try to make it simpler so you can do it. And the elasticity substitution is constant. In fact, in the version in which A is 0, the elasticity substitution is 1. The elasticity substitution in the case in which A is 1 is infinity, and in the case in which, A is minus infinity, it's 0. Okay? Because the elasticity substitution is 1 over 1 minus A. You compute the formula, just do the algebra. Okay? That's why we like it. By the way, you know that this was invented, this is a function invented by economists. This was in the period which they were starting to work, and right after Solo. So there's a group of guys, they said, we need, at the time, the only mathematical representation that people had of aggregate production function to tell stories were the obvious one. So linear, A equal 1. Fixed coefficient that had come from activity analysis, okay, and Cobb-Douglas, because Senator Douglas, Dr. Cobb, proposed this simple formula. Everybody remember K at the alpha, L at the 1 minus alpha for constant return, or K at the alpha, L at the beta, or alpha plus beta less or equal to 1 in general, okay, in the 30s. So this is late 50s. People are starting to trying to study theory of production and a bit more general formula. They want to have general formula for everything. And so this is actually the product of 4 people: Ken Arrow, Dorfman, Chenery, and Solo. You'll find the paper of, I think, Review of Economic Studies. And they say, we want to have a functional form that has some properties. constant return to scale in certain cases for return to scale, concave, constant elasticity, and represent blah, blah, blah. And it's okay, here is the formula. Wasn't available to Schubert. Schubert will not use this formula. Okay. Now, how do I get constant return? Well, we already see that alpha is minus infinity. You cannot. So, what did I say? My brain produced the wrong words. What did I just say? How do I get? Right, I meant constant growth. Okay, remember that was the story. How do I get growth forever from this kind of equation? Okay, growth forever means what? Means that I can increase my income without any bound. Good? So let's imagine that that's the world I live, that crazy world like that, this one. Okay, the one on the right hand side. It's just normalized to one person because income growth is income growth. So first of all, it makes you understand that when we talk about growth, we actually talk about growth in income per capita. So it's been useful to eliminate labor because it doesn't really matter the fact that we produce more because we work more and there's more people working. Well, if we were ministry in Rome, that would be a remarkable achievement. Typically by adding people, output goes down if you're a ministry in Rome. But normal human beings, when they add more work, they actually add more output. Okay? So that's not very surprising. It's interesting only if you go into Rome to be a consultant. Other than that. So here income growth means if I use more capital, I have more output. And I use the same amount of it. Okay. Then you say, okay, how do I get more capital? I have to produce and don't eat all the time. Okay. Then you have to start making assumptions, but they're very simple. So let's make a very simple assumption. We can assume 100% depreciation. Why? Because we simplify and we don't have to do the algebra. Trust me, you can try it. We have the one I showed you the other day with 100. Where do I have? See, it's another. The formulas. You can still see, right? This Jesus. Yeah, you can think of the word like this if you want. Right? You people. Okay, output, consumption, investment. You can think there is depreciation. Right? So depreciation means that every period I have to replace a certain percentage of capital. And so this has to be more than MK if I want K prime. But it's actually simpler to pretend that depreciation is 100%. And so output is divided between consumption and new capital. No difference. Divide consumption and new capital, and you just put the condition the new capital is bigger than the old capital. It only boils down to making this A bigger. We're doing theory. If you have to do national income accounting, you need to bring in the depreciation because you're following numbers. And the ISTAT tells you depreciation was 9% of GDP. But here we're just thinking at the story, the theory, so we can imagine. Okay, so I need the output to be bigger than K. Now, how can you do that? How can you guarantee but that's the. You have to think of this as a function. Now again, I would need the board. See, teaching at a distance is a problem. That's why teaching is one of those things that we should keep doing in class, because you need a lot of tools. But try, use your imagination. Can you, everybody, can you imagine how to plot this function? It has only two variables. I can rewrite it. Where is, you can write it as y equal f of x. Okay? So just y equal x. Y is output per capita and x is capital. No? So you can imagine this on the Cartesian axis. X is here on the horizontal and y is here on the vertical. What is that we need? We need that f of x be always larger than x. Let me put a capital. You follow me? If you want to have growth, f of x has to be larger than x. If I always produce more than I put in, it will always be possible to accumulate a bit more. I just consume the difference, right? Between what comes out and what I need to put in. And I keep growing. So, condition for this economy to grow forever is simply that f of x is larger than x. Nothing else. You agree or not? Then the output per capita larger than the input of capital per capita. This is important because we went in two steps, right? We said, okay, you want to talk about growth, but to talk about growth means talking growth in output per capita, right? And then we said, okay, so that's a way of writing it, is to write it like this, where there is a fixed amount, B, that comes out, even if I put no capital. So the function, in some sense, doesn't start at 0, 0. When k is 0 or x is 0, the function has a positive number. But that's not very important. It's a positive number. You're not going to get much out of it. And then it goes up. As I increase x, the function goes up. But if it has always to be true that I can keep accumulating, it has always to be true that this is true for all possible values of, thank you, x. Well, larger than 0, we should add, because the computer is not that smart. Thank you, Google. Okay. And how do you check? Remember, we already also showed that f of 0 is actually larger than 0. Right? So this is certainly true of the origin. It could be equal, huh? Could be equal. Doesn't matter. But we are lucky. In this particular case, f of 0 is actually b, ab. No, a, b at the power 1 over alpha. 1 over a. Huh? So how do I guarantee that given that this is true, and the function has the form I wrote above, so the function has which form? Has the form f of x is equal to a times f of x and equal a times, excuse me, but this is a very variable, I'm not used. this. Power A. We're going to find the plus the Italian people. Where's the plus? Plus B, right? Everything, no, this, other power, 1 over. This is the function, right? So let me simplify. Yeah, that's the thing we need to start, okay? This one. Huh? So how do you prove that this one clearly, right? When x is 0 is equal to what I said, a times b at the power 1 over a. Some positive numbers, 50. How do I make sure that this is also true for every x? It's one simple condition. Somebody online can help me? The guys in class can't figure it.
Derivative larger than 1.
Derivative larger than 1. Right? If the slope of that function is always larger than 1, that's a sufficient condition Now, notice it's not a necessary condition because the derivative could go lower than 1 sometimes and then higher again. But if it does that, it would violate another condition that we tend to put in economics. Again, it's a mathematical condition that we impose because of economic argument, which is what? That there are decreasing returns. Look at this function. This function here says output per capita is an increasing function of capital per capita. So it says the first derivative is positive, which is easy to see because the first derivative is 1 over a multiplied big A, multiply this, which is a positive number, at the power 1 over a minus 1, multiply a at the x at the a minus 1. And that's all positive numbers, so it's positive. But the second derivative of this is second derivative. All right. Can we write the first derivative and the second derivative? The first derivative is, well, I simplify because I know already what it is. So, right. It's bigger. I don't do all the passages. Oof. Right? So this is the first derivative, right? I eliminated the part. So I have to take first the derivative 1 over a, and then this, but the a and a cancel out, right? So I have this. This is a number larger than 0, right? But now if you take the derivative of these, what happens? There is this. And this, either a is 1, but if a was 1, there was no reason to do all that algebra. A was 1, this was just a, the derivative. And the second derivative was 0, right? But if a is less than 1, and it cannot be bigger than 1, why? Because if there is bigger than 1, it does increase in return. If a is less than 1, there is something with a negative sign. So the second derivative becomes negative and the function becomes concave. If the function becomes concave, then its derivative is always decreasing. Now, intuitively, we like that property because the same argument for which we argued that a technology has always constant return also implies that if one of the factors becomes fixed, you remember I said, then there has to be decreasing return in the other. Because in some sense, if I don't change the technology and I keep adding capital per worker, it's like this poor guy, he has 1 truck, 2 trucks, 3 trucks, 6 trucks, a million trucks. He cannot drive a million trucks altogether. You know, the new truck adds almost no productivity. That's our intuition, right? But now we are imposing, or we are requesting, we are asking, could this derivative always stay above 1? So it means that the production function, that you remember the graph that I showed you of Solo? In the first graph where he had the function that always stayed above the 45-degree line? You remember when the professor Lyceum taught you about an asymptote? That's what he taught you. He was preparing you for my class, for Solo. He had Solo in mind. He said, I want these kids to learn Solo. They understand the footnote. And so if you keep working on that, you'll find that under certain conditions, that derivative, even when x goes to infinity, so capital labor ratio becomes infinite, the derivative remains above 1. And you will see that that's possible when a is positive, little a, little a. Remember, little a could be 0, could be a negative number, all the way to minus infinity, right? Depending on the technology, or could be positive, between 0 and 1. If you work out this thing you have here on the board that I wrote, this derivative, and you let x go into x, Italian, x go into infinity, you will see that this remains a positive number. This remains a positive number as long as a is positive. Sorry, this remains a number larger than 1 as long as a is positive. And so that has a meaning, which is the whole parable of this class. What is the a is positive? In the way we built the production function, when a is positive, capital is a good substitute for labor. Right? There's very good substitutability. In fact, when a is 1, it's perfect. But that's a magic word in which you can do things without laboring. But if capital is a good substitute for labor, it means what? That as capital increases, I can keep labor constant, and capital kind of does the things that labor do. Right? Labor does. And so obviously, it's a metaphor, it's a parable, because I'm talking about technological change. Obviously, if the technology is constant, there is no way that by adding machines to a single worker, the worker becomes more productive. It's a stupid story. You see, that's why those guys like Solo and Nikaido and Mackenzie and Hurwitz and for Neumann said, sure, I can get growth forever with constant return, but it's a stupid story. Because in order to get growth forever with constant return, I have to assume that the worker can manage millions of machines without changing technology. That's not possible. But on the other hand, if I think it's a metaphor, then the fact that capital increases is a way of saying that the technology is changing. But the way technology changes is by producing machines that are good substitute for labor. And then the story becomes a movie. Obviously, it's not a scientific, strictly reductionist story. It's a movie. But it's a good movie. It says, look, if nature is such that we can replace human labor with machines, it's possible to get kind of more capital per worker in the sense that this machine that are here in front is more capital than the old IBM machine that used to be a Casalecchio Surreno when I was your age. and we were at the Palazzo dei Pompieri putting things into a big reader of the name, schede, that we type of in the old days, right? Program, punch, files like things, cards, and you put it in a card reader that would send the signal to a big frame, mind frame. It was a Casale di Torreno, Cineca, and then a few hours later, your program would fish out a few numbers. Now you do everything in a second with your phone. It's much better. You use later on your phone. Well, okay, but that's the point. This thing now is a substitute for me and Carlo and Giulio and Domenico and all the others that together we were punching in the thing, because this can do all the work we did there for days and days and days. But obviously, this story is a metaphor. You understand in what sense? So it makes you, but it's a useful one because you study it and you say, okay, what does the mathematics tell me? The mathematics says that I can keep increasing, okay, and productivity doesn't go down if A is positive. And the closer it is to 1, the better it is. And what is that I'm doing? I'm replacing capital labor with capital. Oh, that means that there is good substitutability. So it's a story about if nature is such that certain human activities, certain things that humans do, and also other fixed resources can be replaced by reproducible resources, then I can increase output. Beautiful. There, and I finish, you have a story of growth. It's a story, it's a description, it's not a theory. It says it happens to be the case that nature, literally nature, is such that we can replace L. What is L? Remember what I said at the beginning. I'm going to do this with 2 inputs, but I can do it with 2 million inputs. So L is a stand-in for every input of production that is not reproducible, or that reproduces very slow, like humans, or even slower, like oil and coal and energy and trees and whatever, right? So they can obviously break down lots of production function with different timing. One has a horizon of a century, one of a year, one of 10 centuries, one of a million centuries, right? And so L is that thing that I cannot reproduce. K is all those things that I can reproduce. And if technological change is such that reproducible things are good at replacing non-reproducible things, among which there is human labor, for sure, then I can increase output. That's it. So it doesn't explain what causes technological change. We will discuss that maybe in the next lecture. It doesn't give you a theory of reducing, but it gives you a reasonable way of thinking of what has been going on, which matter of fact is what's been going on. What's been going on is that we found progressively ways of replacing scarce resources. Right? Why is it the Club of Rome got it wrong? You don't know what the Club of Rome is. Club of Rome was a group of scientists and entrepreneurs that in the early 70s say, oh, you know, oil and coal and zinc and copper are running out. Very soon, 30, 40, 50 years, they will start running out of material. So our industrial society will come to an end. Looks like this happened. Why? People just invented a way of replacing those resources we were wasting or consuming too quickly with things that use a lot less. So now we have more oil than we need. Now we don't want oil for another reason, but we got oil forever in some sense. And we got coal forever. We got iron forever. And it's just a matter of substitutability. This is not to say that I believe it will always be like this. I don't. I have no opinion. I have no opinion of what the future reserves. But to the extent we need to tell a story of what happened, the CS gives you the solution. Okay? All right, now we go in drinking because it's 7:05 and beers are waiting. And we'll see you next Tuesday, those of you that are not drinking with us. Bye-bye.